ionization is very low. It has a very, very low percentage of ionized atoms compared to the total number of atoms in the gas. So we know that fire is a partial plasma, but the problem is that it's still really hot, even though it's a very low grade plasma. In fact, anytime you have a plasma, it's usually extremely hot. For example, arc welders that use a plasma generated between two electrodes can get around 20,000 degrees Celsius. Very hot. Another example of extremely hot plasma is lightning. But today my goal is to create a plasma that's actually cold. Okay, so let me explain to you how I'm doing this. So what I have inside here is an electrode. Now at this electrode, I'm building up a very high potential, an alternating current. And so it's building up to extremely high voltages in the tens of thousands of volts. And it's alternating extremely fast. And what happens is it builds up an extremely high potential, so high that eventually the electrons start getting pulled off in the air around it. So it ionizes the gas around it. Now, normally what would happen around this electrode is it would get extremely hot. And it would get so hot that it would be able to burn anything that touches the plasma. But the goal here is now to generate a cold plasma. So basically we want the gas around it to be cold, but still keep the free electrons. And the way that we do that is by taking away the thermal energy of the gas. So what we need is a gas that can ionize very easily, so it can lose its electrons easily, and also has a very high thermal conductivity. And what we do is we flow that gas through here, and as the gas goes through this glass tube around the electrode, the glass tube absorbs some of the thermal energy of the ions. And so we adjust the flow rate of the gas until it's just high enough so that the gas is flowing fast enough so that the atoms themselves don't get to a hot temperature, but they're still ionized. So basically what we're doing is we're taking away the thermal energy of the ions themselves, but not the electrons. So we still have free electrons that are generating a plasma, but the plasma is not hot to the touch because those electrons, even though they're tens of thousands of degrees, their mass is so low that they can't generate a lot of thermal energy when it hits my finger or hits a match. And so basically what we've created now is cold fire or cold plasma. So it's a plasma that has a very high electron temperature, but low gas temperature or ion temperature. And the gas that I'm going to be using to do this is helium. And the reason I chose helium is because helium can be easily ionized, but it also has a very high thermal conductivity. So it can dissipate the heat quickly and it can ionize quickly. So the temperature of these electrons can be tens of thousands of degrees, but still they have such a low mass that they can't transfer their thermal energy to the match to get it to high enough temperature to light it on fire. So you can see here that the cold fire doesn't burn my finger at all. I can leave it here as long as I want. Now, there's actually more than one way to make this cold fire. In fact, a channel called the Thought Emporium, they recently posted a video about cold fire as well. And in their setup, what they did is they had a capillary tube and they had two electrodes alternating current in there, high voltage. And basically it was generating a plasma arc in there and they were blowing argon gas through it. But the circuit itself was contained in there and they were blowing the plasma out the tube. But in my setup, what was happening is that you yourself touching the fire were part of the circuit. Because it was an alternating current at extremely high voltages, basically the plasma was jumping from the electrode itself to your finger and traveling back and forth through your finger and the circuit. Basically, it's the same way that a Tesla coil works or a plasma ball works. You're part of the circuit, you're grounded, and it's at a very high or low voltage. And so when you touch it, the electrons jump back and forth between your finger and the electrode. But either way, the goal in both of these scenarios is to generate a plasma. But you want to be able to keep the ions or gas in that plasma cool while still allowing the electrons to be free. And so basically these hot electrons can't really do much to your finger or a match or a piece of paper that comes near it. But if you have something extremely small like a bacteria or virus, then those high thermal energy electrons can actually damage them. So it can sterilize things but not burn you. In fact, this cold plasma technology is being used today to synthesize different chemicals. It's even used in dentistry. You can sterilize parts of the mouth without burning somebody. So cold fire or cold plasma is a good method to use when you need to sterilize something, but you don't want to burn it or expose it to any chemicals or high temperature. And thanks again for watching another episode.
So we can couple the ICP to mass spectrometer. So in the last we couple ICP to AES, but you can also couple to the mass spectrometer. Because by using this way, we use mass spectrometer to measure the different atomic weight of the different ionized atom, but do not use their emission spectrum, but do not measure them in spectrum. So this is another way. So here from the left side, we already show mass spectrometer can be a detector, and the mass spectrometer is a universal detector because it measures molecule the measurement based on the molecule weight. So but actually the mass spectrometer measures the ionized molecule or ionized atom. So actually it measures the molecule weight over the charge state. Okay, so this is principle of the principle. This is the process. This is an example of how GC-MS system works.
Designed specifically for the unique requirements of gas chromatography applications. These requirements include enhanced selectivity, consistent low detection limits, and robust day-to-day operation. The typical MS description focuses on the extraction of ions from the source, isolation of the precursor ion in the first quadrupole, dissociation of precursor ion from collision cell, and mass filtering of the product ions in the second quadrupole before detection. But let's return to the ion source to discuss processes that are often overlooked. Even for a high-performance source, ionization efficiency as a percentage of molecules entering the source is very low. This means there are many more neutrals than ions exiting the source. So a thorough description must include analytes neutrals and ions, helium neutrals and ions, column bleed neutrals and ions, and many more neutrals and ions from the matrix at concentrations typically higher than the analyte. To simplify the description, let's start with the analyte molecules and ions. Analyte molecules enter the vacuum source from the GC capillary column and begin bouncing off the hot surfaces of the source. Analyte ions are immediately extracted from the source and focused into the quadrupole mass filter. But what about the non-ionized molecules? The electrical fields within the MS have no influence on these molecules. They follow rapid random motion until removed by the vacuum pump. Parallel processes are occurring simultaneously for the molecules from the sample matrix and instrument background like column bleed. The quadrupole analyzer performs the critical task of mass filtering to isolate the analyte's ions from the majority of these ions. Chemical noise often remains after the first quadrupole but the selectivity of MS-MS removes this final source of interference. Again, we ask, what about the large population of non-ionized molecules? Although the turbopump removes many neutrals quickly, some will randomly diffuse into the quadrupole. At the end of the GC separation, the EI source will be flooded with the highest boiling molecules from the sample matrix. Even in a vacuum, these high boiling molecules can contaminate surfaces in the mass spectrometer. A cool surface will accelerate this contamination process. As we think about the potential for contamination, we must not forget helium. The intense flux, high flow of helium ions helps to burn the high boiling molecules onto the surfaces of the source and the analyzer. The cooler the surfaces, the faster the rate of contamination, and the faster performance is lost. For an LC atmospheric pressure source like ESI, metal quadrupoles at temperatures of 100 degrees Celsius are perfectly adequate and commonly used. But for GC-MS-MS analysis, metal surfaces at this temperature will quickly become contaminated. The Agilent 7000 uses a combination of proprietary and patented technologies to avoid contamination problems and ensure robust, high-performance operation. These include an inert source operating at up to 350 degrees Celsius, and quartz quadrupole operating at up to 200 degrees Celsius. With 35 years of MS experience, Agilent built the 7000 around the unique hot quartz analyzer of the MSD, not the cooler metal quadrupole rods used for LC-MS-MS. Before continuing to the collision cell, one more process must be mentioned. An EI source produces a large number of highly energetic metastable helium atoms. These highly energetic atoms follow a random path like any other neutral until removed by the pump. Some will follow a path parallel to the analyzer and have a high probability of traversing the entire analyzer assembly to the HED-EM detector. During the development of the 7000, Agilent engineers realized a small flow of helium added to the nitrogen collision gas was a very effective way to reduce the transmission of metastable helium through the collision cell. We call this patent-pending solution helium quenching. A comparison of signal-to-noise ratio with and without helium quenching shows the benefit of this technology. Helium quenching has no effect on product ion signal, but the neutral noise component is reduced by a factor of 4. This technical breakthrough means lower limits of detection and quantitation. The 7000 MS-MS, an MS-MS system optimized for gas chromatography. From the classical distribution of ions produced in the inert, high-performance source, to the precise isolation of the precursor ion through the path of the hot quartz hyperbolic quadrupole, into the high-pressure hexapole collision cell for efficient precursor dissociation, product ion transmission, and simultaneous reduction of metastables with helium quenching, to the final accurate mass analysis in a second hyperbolic quadrupole field before ion collection at the triple axis detector. 7000 system has been carefully designed to deliver robust sensitivity and reliable quantitative results. The Agilent 7000 quadrupole GC-MS-MS system, an MS-MS optimized for trace analysis of your most complex GC samples, the new standard for GC-MS-MS performance. Agilent Technologies, our measure is your success.
So why the mass spectrometer is quite important for the modern GC analysis? From this video, you may already notice that the MS depend on it's another type of separation method. Just because it analyze the sample based on their molecular weight difference. So actually, this is another way to separate the sample sample and have very high resolution power because it can see the molecule, it can measure molecular weight. So for complex sample, there always have various coeluent from the system. So when you detect peak by using other type of detector, but for that peak, even though this is just a single peak, those peaks may still contain several different kinds of molecules. Also, you just saw in the video the peak, the composition of the peak may contain the matrix, for example, by column bleeding. So if we have no mass spectrometer, we have no way to distinguish them further. So if we use mass spectrometer, we can do the second step separation based on the molecular weight difference, and then detect the quantity. So, and if we use the MS method, we can not only see the composition of one peak, we can also see the because from the video you also notice that they have a collision cell, so we can furthermore collect some specific molecule into fragments. So from fragments we can get their structure information. So that's the very powerful way to do both the quantitative analysis and the qualitative analysis, do some molecular identification. So this is quite important for quite important feature of mass spectrometer. So and the last one is the infrared detector. So we can use this detector to see some polar sample. So this is not quite insensitive for IR, but it is non-destructive. And I should say the most important, at least for this course, FID, TCD, ECD, the first three detector, and the MS spectrometer is the most potent part for detectors. So you should take more time on this part, but you should also know some feature of this this four. Okay. So, but for you should know how to describe their feature and the principles for ECD, TCD, and FID. Okay. You don't need to know the principle or the analyzing principle of the mass spectrometer, but you should know that this one can provide better separation, better separation power, increase the separation as a tandem way, and it can do a very good identification and quantitation, both ID and quantitation. So so now this is some advanced instrument. So in this picture is multi-dimensional gas chromatography, and this is actually this is a 2D 2D GC, and the detector is mass spectrometer. So what is 2D gas chromatography? So generally we have only one column, and then coupled to the detector, but we can still connect another column, and this column also connect to their detector too. So this one is a two-dimensional separation. So if we think so actually we can think the MS, when you couple GC to MS, so this part replaced by MS, and this part is for this part we for MS, it can still use the secondary separation. But for GC, for 2D GC, we coupled two columns, and the separation power, separation sensitivity, generally we choose orthogonal property. Okay, this video has no sound. To build a 2D GC system, actually it's not an easy way, because there is always a band broadening by. So if you consider the second dimension, so this part you need to consider the sample after the separation from the column 1, they have a relative bigger volume. So the injection volume to the column 2 is larger than the column 1. So we cannot get the so this is increase the complexity. So usually we just apply the 2D separation for some very complex separations, complex sample. And based on the same reason, so to build the 3D, the third column to connect the third column become quite hard. And actually, currently there's no mature commercial solution. So this is spectrum. The time, so 3 dimension, one is time, one is mass molecule weight, and one is intensity. So this is so this is how we get. Okay, so this is another strategy. Use a parallel way. So just actually this still a 2D system, but it used but for the second stage, it used three a splitter to split sample into 3 different columns to do the multiple separation. Also, there's a miniaturized GC system. It has a relative lower separation power, but it's quite useful for some on-site analysis, for example, for environmental monitoring, because it's small, it's portable. So here we can see the column here is just have the same size as a coin. So here we can even build the super small column here, very small. So GC chromatography is extensively applied in food science, and actually it applied for the very broad field from the food science, the fluorescent science, also to the pharmaceutical industry, hospital, widely used. So quite important method, and this one also used for the exploration, for Mars exploration. So here is a GC system. So it equipped with 6 GC columns, and the detector is a mass spectrometer here. So this course is about the GC and LC. So we should know the difference and the application field. So also the GC is a widely used node of the compounds can be applied. So for GC, we usually we should it can only separate volatile compounds. And usually we need to keep their boiling point. The compound boiling point should lower than 300 degrees. Some column can resist on 350, but usually we just work under the 300. And those compounds should thermally stable. We don't want them get they break down, they change their state during the separation. In that case, we cannot identify them. So they should thermally stable. So that's also another reason we don't need to develop. It's naturally develop very high temperature resistant column because for most of volatile compounds, when the temperature get high enough, they get too high, they will break down during the high. During those compounds cannot resist on such high temperature, that's not stable enough. So this is the some key point for your selection, which for separation strategy. When you have a sample, you want to which way is the best, which kind of separation is best, get a GC or LC. So LC, in contrast, it suitable for semi and non-volatile compound. So because LC usually operate under 70 degrees, so they can used to separate thermally unstable compounds. So Dr. Hu will introduce this part. And so here is GC. So GC requires volatile compound, but many compounds are non-volatile. So what we can do, we can do some chemical derivatization to change the non-volatile compound to volatile. So we can change, so we can do some chemical modification, and before inject the sample to the GC. So this belong to the sample preparation. So the target is to make the compound, you make your sample for GC separation. So we can we can. So what we can do, we can target to increase the volatility, or increase the stability, right? And so the point 3 actually related to 1 and 2. So we eliminate polar group can in turn can increase the stability and volatility. So sometimes we'll consider the detectability, right? For example, when we consider the detector available, so maybe we may introduce some special group or special elements to help to improve the sensitivity. Also, the 0.5, the same way. So this is why we do the derivatization, because this part is actually belong to the sample preparation or sample pretreatment. So this is not even though it's a very important for GC, but it's not the core of this course. So I just go through just let you know the general process. So usually we do the pre-column, so that what I said before we introduce the sample to GC. So actually there also have post columns. Post column, but generally we just apply some photon chemistry. For example, use some UV to change the sample state. So this is not quite widely used strategy. So mostly we use a pre-column strategy. So there's a comparison before and after the derivatization. We have a great sensitivity and separation. So this one you can see the noise, the signal over the noise, signal to noise ratio is not high. So, but for this one, we can very high signal. So this is derivatized. So generally, we have several different chemical classes, derivatization classes. So you don't need to recognize all of these, and you don't need to remember this. You just know there are several different ways, and maybe you will study this part of knowledge in the sample preparation course. But in this course, you should know. Generally, we need to change their volatility. We want to increase their detector response. Right? So this is some strategy. So this one we reduce the polarity, and so this is an example to increase the to change a non-volatile compound to volatile. So, but this one is a way to increase also to reduce the polarity. So, okay, so I think so. We finished all the info, all the slides for this for the GC part, and we still have a few minutes. I want to give you a very quick review for this course. So I will open the last PPT. Okay, this one, the section 2. The section 1 is actually introductory part. So the core is from section 2. The major part is from section 2, because from section 2 we actually study the partition mechanism, but section 1 help us to understand what is liquid-liquid extraction. So we should know the first and quite important fundamental concept is distribution coefficient. This is a definition. This is still liquid-liquid extraction. Right? It helps us to build the idea of chromatography. So this is how chromatography works. So the slide without any label, without a pound, without a key, meaning this is also important, also the core part. So the slide with key indicates that's the most important. The slide with the pound, after you finish the study, you can distinguish some of the slide, some slide with pound, just is less important, and some of slide just used for the use as the supporting material to help you to understand the relative important information. So you should know how to compare the K or the. So this is a key part. You should know the basic calculation. Okay, then this is quite important, and this is very, very important. You should know how to draw, how to explain. So those simple calculation is required for all of you, and this is the basic formula you need to remember. So this is not important. It's not covered in this class. This will not appear in the examination. And so, okay, I will take 1 more minute to go through the part 3. Okay. So GC, actually you don't need to focus on the detail of the instrumentation. So I almost many pound here. So it should help you to build the smooth transition from the theoretical study to the practical to experiments. So this is not important for this course, but important for your skill. So this is the core part. We still related to the section 2. It doesn't mean that the slide with pound does not appear. Some of the information in the slide with pound will also appears in the examination. Okay, but you know, the slide like this is quite less important. But maybe this one, because this is related to the some more important information, like to this slide. So this one is relatively important. important than this one, right? So this one, just because it's just a little bit hard to understand, but actually this one is important. So this one is quite important, sometimes it's useless, not important. Okay, so I have the. Okay, thank you, all of you. I wish you have a happy Chinese New Year. And after this class, I will upload exercise problem set, and you can do this and help you get a better examination score. And if there's no new strategy released from the university, we will still the midterm examination will start on February 9th. Okay, so thank you. Okay, we finished.